You are 71 kilometers below Jupiter's cloud tops, and the pressure around you just tripled. The temperature is rising. The winds are hitting 500 kilometers per hour. And you haven't even reached the interesting part yet. Nobody has ever sent a probe this deep and gotten data back. The one time we tried, in 1995, it melted. What lies below that point is, technically, one of the great unsolved questions in planetary science. We know what Jupiter looks like from the outside. We have almost no idea what it actually is on the inside. Before we go down, you need to understand one thing about Jupiter that changes how you picture it entirely. It has no surface, not a hidden one buried under clouds, not a solid floor waiting at the bottom. There is no ground to land on. Jupiter is, essentially, a sphere of gas and liquid so enormous that gravity has compressed it into something almost unrecognizable as a planet. It is 1,300 times the volume of Earth. Its mass is 2.5 times greater than every other planet in the solar system combined. And its gravity at the cloud tops is already 2.5 times what you feel standing on Earth right now. Jupiter's atmosphere begins where the pressure equals sea level on Earth. And from there, it just keeps going. The outermost band you can see from a telescope, that swirling caramel and ivory, is made mostly of ammonia ice crystals. Below that, ammonia and water droplets, then water ice. The clouds alone go at least 50 kilometers deep before you hit anything scientists would call clear air. But here is where the descent gets genuinely strange. Because below the clouds, Jupiter does not stay a gas. It starts to change into something for which we don't really have a word in everyday language. And to understand what that something is, you have to follow it all the way down. Around 100 kilometers below the visible cloud tops, the atmosphere has shed its storms and its colors. The pressure is now 10 times that of Earth's surface. The temperature is climbing past 300 degrees Celsius. Hydrogen and helium, the two gases that make up nearly all of Jupiter, are still behaving like gases here, more or less. Scientists call this region the molecular hydrogen layer. It sounds simple. It is not a place where anything simple survives. The deepest point in Earth's oceans, the Challenger Deep in the Mariana Trench, sits at about 1,100 times sea level pressure. At this depth inside Jupiter, you have already blown past that, and you've barely begun. As you keep descending, the pressure keeps climbing, the temperature keeps rising, and somewhere around 10,000 kilometers below the cloud tops, something happens that has no equivalent anywhere on Earth. The hydrogen stops being a gas, but it doesn't freeze into a solid. The pressure is so extreme that it simply transitions. It becomes a liquid while still being extremely hot. In fact, hot and liquid together feel wrong here because on Earth, those two states don't usually coexist at this scale. But Jupiter is not playing by Earth's rules. This liquid hydrogen ocean is thought to be tens of thousands of kilometers deep. No waves, no surface. Just a crushing, churning, superheated liquid that extends in every direction. The pressure at this point is somewhere around 2 million times atmospheric. If you could somehow drop a human being here, they wouldn't be crushed so much as simply cease to exist in any recognizable form in a fraction of a second. But the strangest part of the descent is still ahead. Somewhere around 40,000 kilometers below the cloud tops, the pressure crosses roughly 3 million times atmospheric, and the hydrogen undergoes a transformation that we can now create in a laboratory, briefly, under extreme controlled conditions. The electrons, which normally orbit hydrogen atoms in a fixed structure, get squeezed so tightly that they break free entirely. They start flowing like electricity. The hydrogen stops being a liquid and becomes something closer to a metal, specifically an electrical conductor. This is where Jupiter's magnetic field comes from. That layer of metallic hydrogen rotating with the planet generates a magnetic field 20,000 times stronger than Earth's. It stretches all the way to Saturn's orbit. Auroras on Jupiter driven by this field are larger than Earth itself. The Galileo probe, the one we mentioned at the start, made it 71 kilometers into the atmosphere before the pressure and heat destroyed it in 1995. That is 0.18% of the way to this metallic hydrogen layer. We have never directly observed it. Everything we know comes from physics, from laboratory experiments, and from what Juno's instruments can infer from the outside. Which is why what Juno found when it arrived in 2016 changed the story completely. NASA's Juno mission did something no spacecraft had done before. It flew in a polar orbit, skimming within 4,200 kilometers of the cloud tops on each pass, and it used a gravity science experiment to peer inside Jupiter the way a doctor uses an X-ray. What the data showed surprised the people who built the models. Jupiter's core is not what we thought. For decades, the assumption was a small, dense, rocky core at the center, maybe 10 to 15 times Earth's mass, surrounded by all that fluid. Juno's gravity measurements suggest something far stranger. The core appears to be diffuse, spread out. Scientists are now calling it a fuzzy core, meaning the dense, rocky and icy material at the center may have partially dissolved and mixed into the surrounding metallic hydrogen over billions of years. The core might extend across half of Jupiter's total radius. If that's accurate, Jupiter didn't form the way we thought, and the textbook explanation for how giant planets build themselves may need revision. And we still don't fully know, because getting data out of an environment that destroys everything we send into it is genuinely one of the hardest problems in planetary science. But the next chapter is already being written. In October 2024, NASA's Europa Clipper spacecraft launched toward the Jupiter system. Its primary target is Europa, Jupiter's ice-covered moon, not Jupiter itself. But studying the Jovian system up close, including Jupiter's radiation belts and magnetic environment, will give scientists new data to refine their models of the interior. Meanwhile, the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023 and is en route to the system. It will perform flybys of Europa, Ganymede, and Callisto, and enter orbit around Ganymede in 2034. Neither mission will fly into Jupiter itself. The atmosphere will remain unvisited by anything that survives the experience. But there is a proposal in early planning stages for a dedicated Jupiter atmospheric probe, a concept similar to Galileo but designed to go deeper, ideally past the 100 bar pressure level where the Galileo probe was destroyed, and potentially down into the water layer that may hold the answers to some of the oldest questions about the planet's formation. If that mission ever flies, we may finally see what is down there. Jupiter has been orbiting the Sun for 4.5 billion years, and in all that time nothing has reached its core and come back to tell us what it found. We've inferred it, modeled it, argued about it. We're closer to the answer than we've ever been.